Poisson process. So for the Poisson process, the Poisson parameter is lambda, and for the time duration of t it will be lambda t. So for the k, number of arrival is equal to k will be e to the minus lambda t lambda t to the power k by k factorial. So for a Poisson process, the mean is lambda t, which is a function of t, which increases if t increases, and autocorrelation will be lambda square t1 t2 plus lambda minimum of t1 and t2. That means if t1 is greater than t2, then it will be lambda t2, and if t2 is greater than t1, then it will be lambda t1. Okay, and it is mainly used to model the number of customer arrival in a shopping center or the number of call arrivals in an exchange. Poisson increment is if a Poisson process starts from time t and goes for the duration of c, so the ending time is t plus c, then the Poisson increment is defined as x of t plus c minus x of t divided by c. So yt will be in the shape of n by c if probability of x of t plus c minus x of t is equal to n. So then the probability function is like e to the power minus lambda c to the power n by n factorial. Okay, in a Poisson increment the mean is lambda, which is not a function of t, and the autocorrelation is also not a function of t, it is just lambda square if the time duration is t1 plus c is less than t2, which means the time durations are disjoint. But if they are not, then it's lambda square plus c minus lambda t1 minus t2 by c square, which is a function of the time difference after all. So for a normal process, the expectation of xt is equal to eta of t, which is a function of t, and autocorrelation rx t1 t2 is a function of x t1 x t2's expectation. So we can say that for normal process, the mean and correlation both depends on the time from which the data are taken. Whiteside stationarity has just two properties to be fulfilled, which is the expectation has to be eta, which is constant, not a function of time, and the autocorrelation will depend only on the time difference tau. Okay. So an independent independent property is just let's take the values of xt, where the t's are taken as t1, t2, and up to tn, which are in increasing order, and the increments xt1, xt2 minus xt1 up to xtn minus xtn minus 1 will be independent and disjoint. That's the definition of independent increment. The Markov process is a process where the present value is only defined by the single previous value. So the probability of xt1 less than x1, which was which in the conditional probability, which was dependent on up to all the previous values, will now just can be written as the conditioned on just the past value, single past value. And then a simple example is coin tossing, where we start from 0, and if we get a head we go up by one value, and if we get tail we go down by one value. So for any present value we can just look at the past value and determine where our position will be. Strict uncertainty process is a process where if we shift the time axis, if we shift the signal to the time axis, we get the same result. So the CDF, joint CDF, when the times are t1 to tn, if we shift the time from t1 plus c to tn plus c, we get the same distribution. A Gaussian process, a wide sense stationary Gaussian process is a strict sense stationary process. That's the simple example. And for white noise, a white noise is a signal is a white noise if nt1 and nt2 are uncorrelated whenever t1 is not equal to t2. That means whenever we are taking the signal at different times, the signals will be always uncorrelated if we take two samples from two different times. Okay. So by definition, the expectation of nt1 minus eta t1 into nt2 minus eta t2 will be 0, and the covariance of t1 t2 will be an impulse which has a value only at the 0 point. That means when the time difference is 0, when we are taking the value, we are taking the two values on the same time, only we get the covariance correlation coefficient at only that